Hello, in this lesson I'd like to show how an exponential, or the inverse of an exponential function, is it's what we call the logarithmic function. So in this table over here, real simple, y equals 2 to the power of x. We can tell it's exponential because our exponent is our independent variable, and our dependent variable would be the result, y. And from the table here we can see when x is negative 2, it's going to be 1/4. And from the graph here, this black graph, x is negative 2, our result is 1/4. If x is negative 1, it's 1/2. If x is 0, it's going to be 1. Again, one of the properties of exponents, anything to the power of 0 is equal to 1. And we can see the progression in the table as well. We multiply by 2 as x increases, because essentially what we're saying is we're multiplying by another factor of 2 as we go down the sequence here. And to do the inverse, what we've seen in the last lesson is that we would just interchange or exchange the x and y. So if we're looking at a new table here, okay, we have, let's change this the font of this. Okay, so if we have x and y, we would just simply exchange. So 1/4 would be negative 2. 1/2 would be negative 1. 1 is 0. 2, 1. 4, 2. And lastly, 8 would be 3. So our domain and range have changed. Originally our domain went from negative 2 to 3, and our range was in the interval of negative 4 to 8 if we were just going to start here and end here, and likewise here. And the graph, the red graph here, is our inverse. We can see that when x is negative 4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0, and so on and so forth. And we can also, in our function notation for this, we would interchange the x and y. So we would say simply x equals 2y. And that's what we have here. Another way to look at this, to tell that one graph is the inverse of the other graph, is if we have this line here, and that line is y equals x. Okay, so when x is 1, y is 1. When x is 2, y is 2, and so on and so forth. So we have matching coordinates here, and if we could imagine that this was a piece of paper and we folded the paper along this dotted line, our exponential function would be transposed onto our inverse function of that exponential function. So that's another way to kind of check that one graph is a reflection of the other graph. And a real good way is to look at the intercepts here. If this is our intercept right here, and that's our intercept right there, they are just interchanged. 0, 1 point interchanges with 1, 0 point. Again, a little more information about looking at inverse functions. So what we want to be able to do is ask the question for the exponential function and the inverse of that. And if we're, for the exponential function, we're asking the question, what is the result when the exponent changes. So we're asking here, when exponent x changes, our independent variable, what will our result be? Okay. Now, likewise, if we're looking over here, let's see, get a different color. The logic will change from here to here. So result and exponent, those terms would just interchange just like our y and x. So the question that we're asking here for our inverse is, what is the exponent when the result changes? So we have different things going on here. Okay. So once again, from table to table, to find the inverse, we interchange x and y. From formula to formula, we interchange the x and y as well. And the questions that we're asking here is, we're asking what is the result, or what is the y, when the exponent changes. But in the inverse, we're asking what is the exponent when, and that should be e, when the result changes. So what we're looking at now is, how do we represent this as a function? How do we get it so it's equal to y now? We're looking for what that exponent is. So we get a whole different set of notations here. And what this becomes now is log base 2 of x, which is the result, equals y. Now it's more into terms of finding out what y is, or what our exponent is. And this gives us the form, and it's also in your book as well. If you have the exponential function, a, some result, equals b, your base number, raised to an exponent, that is going to be the same thing as log b, your base, of a equals x. And a quick example of this would be, let's see, let's bring this down a little bit. Okay, so if we're looking at this, let's look at something that we've seen before in the past. Let's say we have 8 equals 2x. Well, this is a special case where we can use what? What are we looking for? If we're looking at 8 and 2, we should be asking ourselves, okay, is there some connection, some base, or some way to rewrite this? Well, 8 can also be expressed as 2 to the third power, which equals, 2 to the x. So now we have the common base. So if the common base is 2, and what can we say about the exponents? Well, they should be the same. So we can answer the question, 3 equals x. So we know that as well. But let's assume that we didn't know that, and we want to use logarithms, the inverse, to ask the question, what is the exponent x when the result changes, or when we know what the result is? So we would write this as log 2 of 8 equals x. And using technology and using other techniques, we will be able to look at finding this answer just just as easily as finding any other, using properties of logarithms that we're going to get into. Now, this one we know the answer is going to be 3. But let's say we have something that is, okay, let's do a different one here. Get a little more space. And let's have, let's answer this question. Let's say it's 7 equals power 2 to the x. Well, if we refer back to our table over here, okay, we know that our output 7 is going to be between 4 and 8. So we know our answer should be between 2 and 3. And it's going to be a decimal, a rational exponent. So in this case, we can't have a common base. So we want to set this up as the log of 2 of 7 equals x. And like I said before, we'll get into how to calculate this using the calculator, using what's called the change of base rule, and so on and so forth. So ultimately, I want to leave you with the question, okay, here. So what, if you guys could discuss this for a minute in your groups, what is the purpose of converting an exponential function to its inverse logarithmic function? What are we looking for?